Okay, so let's start. In the last class, we continued our discussion on basic real analysis. We first saw what open sets are, and then what limit points are. What is the closure of a set? What are closed sets? What do you mean by the boundary of a set, and so on, right? So all of these have visual or geometric interpretations, but we also gave formal definitions of each of these objects. Right, and then we saw the notion of compactness and continuity. At least for our purposes, a compact set, when we're looking at subsets of Rn, a set is compact if and only if it is closed and bounded. Right, so this is the only notion of compactness that we will need. So as long as your set is closed and bounded, it is compact. And the nice feature about compactness is that if you have any function defined on a compact set, any real valued function defined on a compact set, then this has it has a minimum and a maximum, and they're achieved within the set itself, right? After all, our goal is to optimize some particular function. So as long as this function it is continuous, it need not have first or second derivatives. All we need is continuity, and its domain has to be compact, right? As long as we have these guarantees, we know that there is a well-defined maximum and a minimum, right? And then we saw a bunch of examples of different functions, right? And in this class, we'll continue our discussions on basic calculus, and we'll see the notions of the first and second derivatives, because after all, in many convex optimization or generally optimization algorithms, the first and the second derivative are objects that are frequently used. Okay, so let's, you've all seen the first and second derivatives for real valued functions, and also in your vector calculus course, you would have seen this for vector valued functions. But we'll see this in a little more detail in this particular class. All right. So let's start with the notion of the derivative of a function. Right, so suppose you are given a function f from R to R. What do you mean by the derivative of this particular function? What is the derivative of the function f evaluated at x equal to? Yeah, so it's the slope of what? Yeah, so it's a slope of the tangent at that particular point x. So that's the geometric interpretation of the slope of the first derivative, right? So if I have a function f of x, I take any particular point, and if I can draw the tangent, if there's a unique tangent at that particular point, then the slope of this tangent is equal to the derivative. Okay, so if I had to evaluate the derivative, how would I do this? 1 second. Yeah. So, or do you have an analytic formula for the derivative?
Close point to the point of the concentration and then calculate the slope.
Sorry, can you speak up?
It will take an infinitesimally close point to the point under concentration.
Okay.
And then consider the straight line and then calculate the slope of the straight line.
Okay, so basically you are given the point x, right? And this is x. You take an infinitesimally close point, maybe x plus delta x, and you look at the straight line joining these 2 points. Right? What is the slope of the straight line joining these 2 points? So it's f of x plus delta x minus f of x by delta x, and you let delta x to tend to 0, take the limit as delta x tends to 0. This gives the slope if this particular limit exists, right? Okay, now how do we generalize this to higher dimension? So let's try to visualize a function in higher dimensions, right? So let's say I give you a function on R2. I have a function f from R2 to R. Right? I want to generalize this notion of the derivative. Yeah? Okay, I can define something like a partial derivative. Right? So basically I take the derivative only along one coordinate. So this is f of x1, x2. Now if I fix an x1, if I fix a particular x2, I look at the partial, I view as f of x1 comma x2 as a function of x1. This is a function from R to R, and I can similarly therefore define the partial derivative dou f by dou x1 of evaluated at x1 comma x2. Right, and this is basically the limit as delta x1 tends to 0 of f of x1 plus delta x1 comma x2 minus f of x1 x2 by delta x1. Right, and similarly I can also define the partial derivative dou f by dou x2 evaluated at x1 x2. Right, so in some way you can view this in the following manner. So you have this function f. So it's some surface, right? You take a particular point x1, x2. If you fix a particular x2 and you look at the function as a function of x1, it's some particular curve, right? And the slope of that particular curve. So essentially you're taking this surface, you're cutting a plane, right? And you view, once you cut the plane, the intersection of the surface and the plane gives you a curve, right? The slope of the curve of this particular curve evaluated at x1 gives you the partial derivative dou f by dou x. Right? Makes sense? Similarly, you can do the same for x2. Right? Now, instead, suppose I want to cut this plane in some other direction. What do I do? Right? So I have this surface. Right? I take a plane which is parallel to the x1 axis. Right? And it is, so let's try to visualize this. So I'm looking at R3. This is my origin. Let's say this is my x1 axis. This is my x2 axis. and this is my y-axis. I take a plane which is parallel to the x1 axis, right? Of course, it extends all the way up to infinity, but it perhaps this hits the x2 axis at some particular point, right? So this is the point x2. Maybe I should have used some other notation. Okay, let's say this is my x1 axis, this is my x2 axis, and this plane intersects the x2 axis at a point x2 prime. Right? Now I have this surface and I look at the intersection of the surface with this particular plane. Correct? That gives me a curve. Right? And I now choose a particular value of x1, maybe this particular point. Yeah. Okay. So firstly I have a surface, a function f of x1, x2, right? So that looks like a surface. Think of it like a bowl. Correct? Now I want to look at how the function behaves as a function of x1 alone. I fix a particular x2, right? Let's say x2 equal to x2 prime, and I want to see what this looks like as a function of x1. Now geometrically, what am I doing? It's as though I'm taking a plane which is parallel to the x1 axis and intersecting with this surface, right? That's exactly this curve that I'm talking about. This is f of x1, x2 prime. Correct? Now, if I take one particular x1, right, it gives me some particular point. Let's say I take x1 equal to x1 prime, which is perhaps, so this is the value of f of x1 prime, x2 prime. Okay, the setup is clear, right? Simple enough. So basically, if I evaluate the derivative, or if I take the slope of the tangent, right? So what is this tangent? It's basically a straight line passing through this plane, right? And it is tangential to this particular curve. If I view it in 3 dimensions, basically I'm taking a straight line which is parallel to the x1 axis, right? And evaluated at x1 prime, x2 prime. Does that make sense? Sorry? It will be parallel to? So I'm picking a particular value of x2, right? I want to see what is dou f by dou x1.
X1 will parallel on the plane that's parallel to x1. It won't be parallel to x1 itself.
It won't. Okay, sorry. That's right. So it's parallel to the x1 y plane. Yeah. Perhaps I should be more careful with this. You're right. So it's parallel to the x1 y plane. Everyone agrees? It's on this particular plane, right? And this plane is parallel to the x1 y plane. Correct? So this cuts the x2 axis and is parallel to the x1 y plane. Okay, it's fine. So in other words, I'm taking this straight line which is tangential to the surface, but at the same time it is parallel to the x1 y plane. Correct? Similarly, if I look at dou f by dou x2, right? So this is the slope of a straight line which is tangential to my curve, right, which is tangential to the surface, but is parallel to the x2 y plane. Correct? So in other words, I'm picking these two directions and I'm trying to find the slope of a straight line which is tangential to my given surface. Correct? Now suppose I want to evaluate the slope of a tangent along any other direction. What would that be equal to? Okay, in what way?
If we can express the direction in terms of x1 tap next to that, then
Okay.
Linear transformation.
Okay, what linear transformation of what?
Sections at x1 and x2. X1 dash plus b dash.
Okay, so how do you represent a direction? Okay, is it any sum of vectors? Is it any sum of the basis vectors?
Gradient.
We've not even defined a gradient yet. But we're just talking about vectors, right? I want to represent a direction.
Okay, the sum of vectors such that the norm is 1.
Yeah, what is it called? It's a unit vector, right? So a direction is basically represented by a unit vector. Right? Right, so you take any vector u, in this case in R2, because we're looking at functions of on R2, such that the norm is equal to 1. Right, so that gives me, that in some sense represents a direction. Correct? Okay, now I've specified the direction. If I take the direction along the x1 axis or along the x2 axis, I know exactly how to evaluate the slope of a tangent. Correct? Now basically I want a straight line which has this particular direction and is tangential to the surface. What will the slope of the tangent be equal to?
Some of the derivatives of each individual direction.
Can you be a little more specific? So how would I evaluate it? Okay, and what is that equal to? Correct. So it's just the dot product of so that would be the directional derivative along the vector u, and that would be essentially the inner product of u along with this vector, which is dou f by dou x1, dou f by dou x2. Right? But how did you get this?
Projection of tangent along the direction.
Sorry, projection of?
Projection of the tangent.
The tangent along that particular direction. Okay. I don't see here any other responses.
projection of unit vector on the plane formed by the two derivatives.
Okay. Does everyone agree? Okay, so suppose I had to say derive this analytically, right? How would I do it? So what would the derivative be equal to? Of what linear transform?
The derivative at that point is
Okay.
transformation from R to R.
Okay.
The matrix representation is this.
Which?
And then the derivative.
Okay.
1 by 2 matrix.
Okay.
That's how we will get it. And the inner product is using the dot product.
Yeah, but how do you derive this?
Start that given at any point when you want the direction of the tangent, you can
Okay.
express that as a sum of the derivatives along, like that itself is a vector. You can represent that as a sum of the two basis vectors here. That is x1 and x2.
Okay. I know. Yeah, but I haven't defined the Jacobian yet, right? I'm trying to derive what the Jacobian is. Right? So if I had to get the directional derivative, right? Again, we've seen for a given plane curve, this is the derivative. Right? You all agree that this is the slope of a line passing through this particular. Right? So similarly, if I give you a particular direction, what would the derivative be equal to? Yeah. So I take a point x1 comma x2. Right. I give you a particular direction. So essentially,
X plus p8,
you have f of, okay, say x1 plus,
x plus p8. Same thing, x component value 1 to 2.
okay, x,
X plus p8,
sorry, what?
p8, p8.
P. What is P?
P in any direction.
Okay, P is your direction. So right now I'm taking U as my direction. So U, H is what?
Delta.
Okay, it's a scalar. So let's say it's delta U.
Minus minus fx by delta.
Correct.
This goes to
So you're taking the limit. So everyone agrees that this is what we want to compute, right? So this is equal to the directional derivative, correct? Okay, how do I evaluate this? So we take a particular point x, right? So from this point x, so what is x plus delta u?
delta times in u direction from this.
Correct. So u gives you a direction, right? So x plus delta u is, in other words, you're taking a delta step from x along the direction u. Agree? Right? So that's how we get this. Correct. So I'm basically moving in the direction of u by an amount of delta. Correct. So basically I'm taking 2 points on the function f, right? One at x, the other at x plus delta times u. Right? And the slope of the line joining these 2 points basically is this particular quantity, and I'm letting delta to tend to 0. So this should give me the directional derivative. Fine. Okay, now how do I evaluate this? How do I get this from this?
You can use the basis instead of u.
Okay.
Instead of u, you can get the basis 1 way, suppose. Then you will get del f del x1.
Fine.
And you take 0 1.
Okay.
You will get del f del x.
Okay.
And this is how you will get this.
But from that, how do I get this?
Del f del x1 equal to the limiting number of this side. When you take the basis as 1 0.
Yes. So when you take u to be any of the standard basis vectors, I get del f by dou f by dou x. Yes.
The second component you will get 0 using 0.
Okay. Then how do you get dot product with u?
Because if you take U as the sum along those x1 and x2 directions,
Mhm.
you can take it as a linear combination of those two.
Okay. But in some sense, you're saying that this is linear in U, right?
So you can just say that the derivative with respect to the component of u along x2 will have zero derivative with respect to x1.
Okay.
So if you expand it directly, you can just expand that. You can expand the dot product and see that it will become zero for t, say u x1, u1. So if you take the component of u along x1, u1. You write it as u1 plus u2.
Okay.
Then
It's U1 comma U2, right?
Yeah.
Okay.
Yes, and then you take the derivative of that sum u1 comma u2 with x1 and x2 individually.
Okay.
So then u2 with respect to x1 becomes 0, u1 with respect to x2 becomes 0. You take the dot product.
Okay.
Okay, this is it.
Sure. Perhaps that's a better way. So let's take f of x1 comma. So this is what we have, right? This x2 plus del u2, delta times u2 minus f of x divided by delta, correct? So what does the derivative mean? When you say that this is f prime of x is equal to this, what this means is that you can write f of x plus delta x as f of x plus delta x times f prime of x plus some e of delta x, where this quantity e of delta x goes to 0 faster than delta x. So this is in some sense the Taylor series, or at least the first two terms of the Taylor series approximation, correct? Right, so or to be more precise, the limit as delta x tends to 0, e of delta x divided by delta x, so this is equal to 0. Yeah. Yeah, so I'll just go there just. Okay, do you agree that these two are equivalent? Okay, so now let's come back to this. Yeah.
Minus x1 comma x2 plus u2 plus x1.
Slowly. fx1.
You write the first x1 plus u first.
Okay. F
x1 plus u1 is
1 plus u1. Okay. Delta times u. Okay, so you want delta times u, x1 plus delta u1, x2 plus delta u2
minus
yes
x1 comma x2 plus
okay
delta u2
x2 plus delta u2
plus x1
plus
plus this. The same. Yeah.
which one?
This one. Second term. Subtracting that.
Okay, the same thing. Yeah.
Then minus x1 minus
Yeah.
by h.
The whole divided by.
Then you break it.
Yeah.
Plus 2.
Sure. The approach is right. Same approach, but maybe I'll write it a little bit differently. Right? It's the same thing, no difference. But right. So using what I had just written, I can first view this as a function of x2. I keep x1 plus delta u1 as it is. I can write this as f of x1 plus delta u1 comma x2 plus dou f by dou x2 times delta u2 plus some function of delta, right? I'm just taking this function, expanding about x2, correct? For a given value of x1, I'm just expanding this function as a function of x2. Minus f of x1, x2 whole divided by delta. Okay, I'll repeat the same thing, right? Now I can view this as a function of x1. I expand about x1. x2 plus dou x2 delta times u1 plus
X1.
sorry,
So it's no, go ahead.
yeah, so dou f by dou x1 delta u1 plus dou f by dou x2 delta times u2 plus some other function of delta which falls to 0 faster than delta, minus f of x1 x2 whole divided by delta. Sorry, yes, yes, down here. No. So I first expand this at x1 plus delta u1 comma x2, right? So I fix the first coordinate, right? I expand about the second coordinate, right? So I get f of x, x1 plus delta u1 comma x2 plus dou f by dou x2 times delta u2. Okay, then I fix the second coordinate and expand about the first coordinate, right? So I get f of x1 comma x2 plus dou f by dou x1 times delta u1. Okay, but these two cancel and therefore I get u1 plus dou f by dou x2 u2.
Sir, could we do something different? Could we like apply a linear transformation on the point such that it lies on one axis
Yes.
and then get the derivative and then put it back?
Oh, so you mean view it as a composition of two functions? Sure. You could, but in a sense that is what we are doing, right? So the main point over here is that the derivative, in some sense, is a linear transformation. Correct? That is precisely why you can do this. So more generally, right? Suppose that you take f of x plus some h, take any two vectors x and h, minus f of x some d x times h. So essentially, what is the derivative trying to do? It's trying to get a first order approximation of your function. Correct? So basically at x, you're trying to approximate f by a straight line, trying to find the straight line. Correct? The slope gives you the derivative. In general, if you have a multivariable function of, so basically f can be from Rn to Rm. Right? So if it is possible to find an m by n matrix D for which this particular quantity tends to 0 as the norm of h tends to 0. Right? Suppose that this limit exists and it tends to 0. Right? The limit is equal to 0. Then we say that f is differentiable at x, and the derivative is equal to d. Right? So note that this D is going to be an m by n matrix. Now this D depends on the point it is evaluated, of course. So we'll call this df of x. And what are the entries of df of x going to be equal to? These will simply be dou fi by dou xj. Right? Remember that f is a function from Rn to Rm. So in other words, you can view this as m different functions, each a function of Rn. Right? So in other words, the partial derivative of the ith component of f taken with respect to the jth component of x. Okay? So again, can you verify that for if f is a function from R to R, then this reduces to the standard derivative? Would you agree? Yes, you would agree. If f is a function from Rn to R, so m is equal to 1, what does this reduce to? Not exactly the gradient, it's going to be the transpose of the gradient. Typically, you take the gradient to be an n by 1 vector. Again, depends on how you define it. But typically, you take the gradient to have the same dimension as x. Right? Whereas in this case, it's not going to have the same dimension as x. It's going to be a 1 by n vector. So if f is from Rn to R, then this is simply the gradient of F transpose. Right? So this is the definition of, this is the Jacobian. And this is also sometimes called the Frechet derivative. Okay, and again for the derivative you can have a host of properties. So firstly, the derivative is a linear function of F. So if I have two functions which are also differentiable, F and G, both differentiable, then the derivative of say alpha F plus beta G, this is going to be alpha times the derivative of F plus beta times the derivative of G. Also, what is perhaps more interesting, more relevant for us, and equally useful is the following chain rule. So suppose I have a function g from say Rm to Rk and f from Rn to Rm, and have h of x to be say g of f of x, then the derivative of h evaluated at x is simply the derivative of g evaluated at f of x times the derivative of f evaluated at x. Okay, so these are all properties very similar to what you've already seen in high school, right? But sometimes, okay, so maybe let's do a quick example. Suppose I give you the following function, right? Let's take, okay, what would be the derivative of f of x equal to say x transpose ax. So this is a function from Rn to R. To ax, are you sure? How did you get that? Okay, how do you get that? I don't want you to use the formula. I mean, use what you've already seen, right? The simplest way is, okay, how do you, what is the derivative equal to? You basically just have to compute the Jacobian matrix, right? In this case, it's just a vector, correct? So what is x transpose ax equal to? This is a nice simple function. So yeah, it's quadratic, but how in terms of xi and xj, what is it equal to? Correct. So it's going to be summation I equal to 1 to n, summation j equal to 1 to n, aij xi xj. Does everyone agree with this? Okay, great. So what is dou f by dou xi equal to? Maybe let me just change the indices because it's very easy to get confused. I1 j1, I1 j1. Okay. Now I'm taking the partial derivative of f with respect to x. Right? Let's say xi. Right? And xi can appear both on the left as well as on the right. So you have to count things carefully. Right?
Summation.
Yep.
Only summation j1 from 1 to n.
J1 from 1 to n.
ai j1
Ai j1
x j1
x j1.
plus
Okay.
summation. Plus summation. I1 equal to, okay, say I1 equal to 1 to n. I1 j x xi1.
Okay. Is this a linear function of xi? Sorry, is this a linear function of xi? You keep all the other xj's constant. Right?
Keep all the other.
Yeah, you fix all the other xj's.
Then do a square.
There should be one square term. So where did the square term go here?
The square term is being counted twice.
Exactly. The square term is in fact being counted twice. So this would be j1 equal to 1 to n, but j1 not equal to I of this quantity, plus I2 equal to 1 to n, I2 not equal to I of this quantity, plus 2 times x I times, sorry, 2 times xi I times ai. Sorry, 2xi times ai. Right? So you can verify that this is in fact is the partial derivative. But what is this equal to? Yeah. So this is a dot product of something with the x vector. It's a sum of two dot products. What is this? Yeah, so this is the dot product of the ith row with the vector x plus the dot product of, actually this should have been careful, right? So the dot product of the ith column of A with the vector x, right? So in other words, this is the sum of the dot product of the ith row of A with x plus the dot product of the ith row of A transpose with x. Right? So the gradient of f would therefore be equal to A plus A transpose times x. Right? So it's not equal to 2 times A times. If A is symmetric, then this reduces to 2A times x. So things can be a little different when you go to higher dimensions. Any questions? Okay, so this is fairly, I mean, if you have a linear function or a quadratic function, something which is very nice, where you can separate it in terms of xi and xj, it's fairly simple to compute the expressions for the gradient or the derivative, right? But what if we have a more complicated function, right? For example, one function that we'll frequently use, which comes up in communication, signal processing, and so on, is the following function. So suppose I look at functions on matrices, right? So I have this function from R n by n to R. Again, maybe not all of Rn by n, but I'll define it over a subset of the set of all n by n matrices. In particular, what I call the set of all positive definite matrices. Okay, so f of x, any matrix x, is going to be the log determinant of x. Okay, or basically some function of the determinant of x. Now, polynomials are easy, you can find the derivatives, but suppose I give you a complicated function like this, how would you find the derivative? And we will need the derivative of this as we proceed. Okay, fine, I can, so log is still perhaps manageable, but what about the determinant? Can you get a general expression for the determinant of a matrix?
Analytically, if you use the expression for the determinant, it will be boiled down.
Okay, I want a nice expression, right? So you can, sure, they can perhaps use it to evaluate it. For a small matrix, fine.
You write inverse is adjoined by that, right?
Okay,
So could you write determinant is A times adjoint of A?
determinant is A times adjoint of A.
Proceed from
Wait. So, no, so wait. So you're saying, so the inverse of A is equal to adjoint of A divided by the determinant of A. So the determinant of A is whatever, adjoint of A times A. Okay, which means now you now have to find the derivative of the adjoint. Adjoint. Yeah. How do you do that?
Can we like diagonalize it and then
Okay. How?
like, because it's positive definite,
Uh-huh.
we have like a diagonalization.
Okay.
So if we can find, we can enter B transpose B or
Okay, but it will also depend on the eigenvectors, right?
but that we can find because we have
You have X, true, but is it possible to do it more generally? I mean, it's still not an easy task, right? Because the eigenvectors, I mean, they're not universal. They depend on the matrix X. Correct? And even differentiating those is not going to be easy. All right. So I'll evaluate the derivative of this. I'll try to compute this. There'll be some gaps in my calculations, right? Because we've not seen positive definite matrices yet. We'll see some of their properties as we go along. Some of you have already seen positive semi-definite and positive definite matrices, but some properties of positive definite matrices are the following. So the first property is that they have all their eigenvalues are positive. Right, and of course that's important. That also implies that the determinant is always positive. Right, otherwise this quantity would not make sense. Secondly, there's a notion of a square root of a matrix. So there exists some matrix I'll call it x to the half, which is invertible. And you can write x as x half times x half. Right? So we'll take this as a given for now. Right? So let's go back to our definition of the derivative, right? So we said that it's a derivative if we can write f of, let's take f of x, maybe x plus delta x. Take 2 points, x, and let's call the other point z. So I want z to tend to x. And I'll try to expand about x. F of x plus in other words, I can write this as, yeah, so it's the dot product between d and z minus x plus some error function. Right, so what is the derivative trying to find the derivative? I'm trying to find the best linear approximation to f of x. Right, so I'm writing f of z as f of x plus some linear function of z minus x. Correct? Okay. So if I look at log determinant of z, so this is log of determinant of x plus delta x, right? I somehow want to write this as f of x, that is log determinant of x, plus some inner product between a matrix and z minus x, plus some error term. Now, what do I know about x? I know that there exists a valid square root. So I'll write this as x power half times x power half plus delta x. Okay. just manipulated these symbols around, nothing more, right? I've written x as x power half times x power half, x half times x half. I've taken x half out on one side and this x half out on the other side. So essentially I get x half times I plus x minus half, so the inverse of x half times delta x times x, the inverse of x half, whole thing times x half. Okay. But what is the determinant of a product of three matrices? The product of the individual determinants. So this is log of determinant x half times determinant of I plus x minus half delta x x minus half times determinant of x half. Right, but what is that equal to? Yeah, so it's log of this quantity plus log of this plus log of this quantity. Plus but what do these two give me? Plus log of determinant of x. Okay. So as long as I'm able to expand this as some linear function of delta x, I'm kind of done. Right? So let me look at this particular matrix over here. Right? Suppose this has eigenvalues, say lambda 1, lambda 2, up to lambda n. What would be the eigenvalues of I plus this? 1 plus lambda 1, 1 plus lambda 2, 1 plus lambda 3, 1 plus lambda. Right? So what would the determinant be equal to? The determinant of this matrix be equal to 1 plus lambda 1 into 1 plus lambda 2 into so. So this would be equal to log determinant x plus log of the product I equal to 1 to n 1 plus lambda I. Correct? So as delta x tends to 0, what would happen to the lambda i's? So delta x is a matrix, right? It's a perturbation around x, correct? As delta x tends to 0, what can you say about the eigenvalues, lambda 1, lambda 2, and so on? They would tend to 0, right? So as delta x tends to 0, this matrix x minus half delta x, x minus half, this would also tend to 0, correct? So therefore the eigenvalues will also tend to 0, correct? Now what can you say about log of the product of 1 plus lambda I. So this is log determinant x plus, I mean, in any case, this is equal to I equal to 1 to n log 1 plus lambda I, right? So for x close to 0, can you approximate log 1 plus x? It's of course close to 0, but it's approximately x, right? X plus some error function which decays faster than x. Right, so that's what I've written, this approximately equal to but what is this equal to?
Yes, sir.
It is the trace. Lambda I, this is the trace of x minus half delta x times x minus half. But what is trace of a times b? Is the trace of b times a. Agree? So this is equal to the trace of x minus half times x minus half times delta x, or the trace of x inverse times delta x. Right? So for matrices, the product of, so the inner product between A and B, two matrices A and B, you can write it as the trace of A times B. Right? So in that case, what would you say is the derivative? Okay, so this is what we have, right? What can we say about f of x plus delta x? So this is equal to f of x plus this quantity, the trace, which is the inner product between x inverse and delta x. So what is the derivative equal to?
We take the limit as delta.
Yes.
Because delta equals to 0, f of x plus delta x minus f of x by delta x.
Correct. But what is that equal to? I have this here, right? Okay. So again, recall what is, so this is the general definition, right? So it's f of x plus h minus f of x minus inner product between something times delta x divided by norm of delta x. So in this case, what will the derivative be equal to?
Inner product of x was over delta x by delta x.
Okay, that doesn't really make sense, right? Yeah, it's x inverse, right? So this is going to be equal to x inverse.
How do we go from trace to the
That is the inner product for matrices. Okay, now there are a few things that I sort of skipped over. For example, we've not seen properties of matrices yet, right? But this example is just to illustrate that when we are viewing functions over Rn, there are a lot of subtleties to take care of. We want to evaluate, for example, a function which we so commonly use, right? The determinant of a matrix. This doesn't have a nice closed form expression that we can easily manipulate, right? You can get a closed form expression, of course, but it's not easy to manipulate, right? But even then, if you look at the derivative, this has a very simple expression, it's just the inverse. And if you view this, I mean, this is in some sense natural, right? Because what would be the derivative of log x? It's 1 over x, right? And that in some sense is what we are getting over.
So again, how do we define trace to be the inner product? What happens?
So the trace is an inner product. It satisfies all the properties of an inner product. And that is the notion of inner product that we're using in this particular definition.
Different inner product than.
It's a different inner product than the standard dot product that you see. So that is why there are some notions that we haven't visited yet that we'll visit when we talk about linear algebra and matrices. Right? For matrices, this is the definition of inner product that we use. Okay, any questions? Yeah. Delta x is also an n by n matrix, yes. The trace will be a real number, yes. Yes. Can you speak up?
Trace is a real number and we have considered to be the product of
Yes.
this inner product is again an n by n.
No. So the trace is a number, right?
Its definition is
Yeah, so that by definition, the inner product between two matrices is the trace of the product of those two matrices.
it's not just simple.
It is not simple multiplication. Because after all, I need a real number for this to make sense, right? Because f of x is a real number. It's a log of the determinant of the matrix. Correct? So the inner product always has to be a real number. Okay? Any questions? Okay, so now now that we've seen the derivative, right, how do we define the second derivative of a function? Yes?
We do the same thing for it.
Correct. So what is it equal to? What is the second derivative equal to? Correct. So it's a derivative of the derivative. This is just the right.
Can you say anything geometrically for secondary?
Can we say
Anything geometrically for secondary?
what is the geometric interpretation of the second derivative of a function?
First derivation, like first derivative we say is a slope of tangent, right?
Correct.
Say about secondary.
So in some sense, you can, of course, one way you can view it as a rate of change of slope in some particular direction. But another way to view it is, okay, the derivative defines another function.
Rate of change of slope, but like we are finding it at one particular point, right?
Correct. So if I shift by delta x, then by how much is the slope going to change? Right? So in general, if we have some function from Rn to R, remember that the gradient given a particular function f from Rn to R, the gradient was an n by 1 vector. Right? So what can you say about the second derivative? So the gradient is basically a function from Rn to Rn. Correct? Yes. Yes. So the second derivative would be a function from Rn to Rn cross n. And basically what this just gives is the Hessian matrix. Right? So just like the gradient, we define del square f. So this is a matrix which is just dou f, dou xi, dou xj. All right, and basically all the properties that we had of the first derivative, linearity and the chain rule, also extends to the second derivative, right? Because after all it's a derivative of the derivative. Right? So in particular, so the chain rule for the second derivative would be the following. Evaluated x, or maybe I should say, so if I say that h of x is say g of f of x, where g is a function from R to R, f is a function from Rn to R, so this would simply be equal to f of x times the gradient of f transpose plus the square f of x times If you just take n equal to 1, then this gives back the standard chain rule for the second derivative that you would have seen in high school.
G goes from say R to some R bar value.
Yes.
If we get n such places, right?
Yes, that's true. So yeah, that becomes a more complicated object to handle, but generally the kind of functions that we are interested in are of this particular form, right? We're typically interested in functions from Rn to R, and you take the composition with another function from R to R. But yeah, all of these generally hold for some function f from Rn to Rm, g from Rm to Rp, and so on. Okay, any questions? Okay, so let's stop here. Hopefully by tomorrow I'll upload a problem set which you can solve. It will mostly involve some of the basics that we've seen and gradients and hessians and so on. So that will also help you understand these topics better, and you'll see the gradients of some commonly used functions also. Okay, let's stop here.